Today, I would like to talk about several latent space dynamics identification framework for data-driven approaches to accurately accelerate computationally expensive simulations. I will be touching upon the concept of interpretability, expressivity, scalability, and physics-informed sampling. Before I dive into the main presentation, I would like to recognize wonderful reduced order model teams whom I was fortunate enough to work with. Plus, without these collaborators, I wouldn't be able to present what I am presenting today. So big thanks to all of them. Physical simulations play an important role in modern science, but they can be computationally expensive as shown in this slide. This is unfortunate for many decision-making applications such as design optimization, uncertainty quantification, and inverse problems. Because there, we need to run these both physical simulations many times as we explore parameter space. Therefore, we need a fast simulation capability, and we will achieve this goal using data. Well, then how can we accelerate the existing physical simulations with data? The most straightforward way would be to use a neural network to directly relate input and output data. For example, we have trained a conditional generative adversarial neural network to relate permeability and pressure fields for porous media flow simulations. We were able to get very accurate predictions and a high speed up. However, this is a black box approach because we blindly relate input and output data with some neural network structure, which we do not have much control on and which we do not understand deeply. So once the neural network is trained with some given data, it is what it is. In that sense, it lacks interpretability and explainability simply because this neural network structure is not familiar enough to us yet. Well, then how can we get an interpretability? We have to somehow relate this data-driven model with what we are familiar with already. The things we have studied for a long time, for example, ordinary differential equations or partial differential equations. To illustrate this fact, let me consider a simple radial advection problem, which is described by a well-known partial differential equations. You solve it using some numerical schemes such as finite element or finite difference methods, then generate simulation data. This data is high dimensional, so it would be hard to fit them directly into some model. Plus, remember that our goal is to build a fast model. To build a fast surrogate model, we better deal with reduced space dimension. So we compress the data, which, for example, leads to the latent space dynamics with dimension of only 3, as depicted with this trajectory graph here. There are two different types of compression techniques, linear compression and nonlinear compression. Either one has advantages and disadvantages, which I will lay out later. But this low dimensional data is a lot easier and more manageable to fit into a model. Which model would you use? We can imitate what Isaac Newton did with orbital motions. Yes, differential equations. We can fit the latent space data into differential equations, for example, linear ordinary differential equations or quadratic differential equations, or even some nonlinear functions such as exponential or logarithmic functions and so on. Then you can solve these little ODEs to predict the solutions very fast. Let's call this procedure LaSDI for convenience, which stands for latent space dynamics identification framework. By the way, if we choose to use linear compression, such as SVD, singular value decomposition, and linear differential equations for latent space dynamics model, then we are more or less using the famous method that is dynamic mode decomposition, so-called DMD. On the other hand, if we use again linear compression and polynomial ODEs, mainly quadratic ODEs for latent space dynamics model, then we are again using the famous operator inference methods. By the way, we know a lot more about ODEs than neural networks, so This approach is, although purely data-driven, it is interpretable. For example, if we happen to know this A hat matrix here explicitly, we can perform eigenvalue decomposition and write an analytical solution for linear ODE in terms of eigenvectors and eigenvalues. For example, if the real part of eigenvalue is greater than 1, then the solution will explode. Therefore, we should make sure that the eigenvalue does not exceed 1 if we know the true solution does not explode. Here, eigenvalues serves as an indicator which tells us why the model fails. If it fails, why the model is successful, if it is successful. So it is interpretable and explainable. Now we want to make this LaSDI framework robustly accurate when the parameters changes. There are many different ways to making the framework parametric. First of all, we only want to deal with latent-based model, not the full order model, which implies that parameterization must be done within the latent space. Let me show you one way of doing it. Here is a parameter space D for its training parameter point. For example, parameter point mu1. We can build a tailored ODE that best describes the latent space dynamics at that point. Note that coefficient matrix A hat depends explicitly on mu1. You can do the same thing for mu2, mu3, and mu4 and mu5 and so on. Then you can interpolate the linear coefficients of the ODE for a testing point mu star. Note that the coefficient matrix A depends explicitly on the testing parameter mu star, as well as all the training points mu1 through mu5. As you can easily imagine, you can apply similar interpolations for other testing points. We have applied this LaSDI framework to the radial advection problem by parameterizing initial condition with two frequency values, W1 and W2. For this problem, we took uniformly sampled training points as shown in this graph 5 by 5, which gives 25 training points in total. For each training points, we generated the high-dimensional simulation data. Then we compressed them to latent space with dimension of 3 using auto-encoder. Then the coefficient of ODEs that fits the latent space dynamical data were interpolated. This heat map shows the relative error on a given parameter space. The maximum relative error was 5.4%, and that occurred along these lines here, right? The LaSDI framework was able to give us a speedup of 200 when compared to the full order model simulations. Decent results, right? But we were not happy about the high relative error concentrated on the particular region of the parameter space, which was here. So this was caused by the uniform sampling. So we needed a better sampling procedure, possibly by incorporating physics information. We have actually developed such a non-uniform sampling procedure that is guided by the underlying physics. When we applied it to the same radial advection problems, we got better accuracy, even though we used the same number of training points, that is 25 training points in total. The heat map on the right here shows relative error distribution on the parameter space when the physics-informed greedy sampling is used. As you can see, the training points were not sampled uniformly. More samples were chosen on the right bottom corners right here, which makes sense because the relative error with the uniform sampling were high on those right bottom corners. With this physics-guided non-uniform sampling, we were able to achieve a maximum relative error 2%. This time, the maximum relative error happens on the left side of the parameter space, which makes sense. So how do we do it? We followed an active learning paradigm where you adaptively append training points while the autoencoder is being trained. For example, you start with 4 corner points in the parameter space, which are marked by 4 empty squares where we run simulation data. Then we check if the number of training points reach the maximum allowed let's say we are willing to spend 10 training points in total. Since we only have 4, we are going to move on to the training of the autoencoder and dynamics identification process. Because the autoencoder and dynamics identification steps must communicate with this adaptive sampling procedure, we combine the latent dynamics identification step into the autoencoder training by adding the latent space dynamics regression terms as loss function terms. So there are 3 terms in total in the loss function. First one here is a typical reconstruction loss for autoencoder, which takes the difference between original high-dimensional simulation data with reconstructed one through encoder and decoder. The second and third loss terms are related to the latent space dynamics regression terms. We go through several epochs to pass, say, 2000 epochs to minimize these 3 loss terms simultaneously with current training data. Then we go back to the sampling where we apply random validation points. At each validation point, we compute the physics-informed error indicator. We use the residual-based error indicator in order to incorporate the physics. We find out where the maximum physics error indicator occurs with the current autoencoder and the dynamics identification model. In this picture, this red point here gave us the maximum error. So we take it as a training data and generate simulation data there and add it to autoencoder training. We repeat this process until the desirable accuracy or the maximum number of training points are reached. If you want to know more details about this physics-informed greedy sampling procedure, you can check out this paper. Or I have a short YouTube video that explains it. You're welcome to check this out. It's less than 10 minutes, so I'm sure you will enjoy it. All right, for the last point, but not the least important, I would like to address the advantages and disadvantages of linear and nonlinear compressions. The advantages of the nonlinear compressions over the linear compressions are many. In general, nonlinear compression provides a better projection error than the linear compression, even though they are using the same latent space dimension. This implies that nonlinear compression has more compressibility or expressivity than the linear compression. Plus, if you compare the latent space dynamics from both compressions, the nonlinear compression tends to give a simpler dynamics than the one from linear compression. This is obviously advantageous in the context of LaSDI framework. To demonstrate that, here we have applied both nonlinear and linear compression-based LaSDI framework to advection-dominated 2D burger simulation. For nonlinear compression, we chose a latent space dimension of 3 and cubic ODE for latent space dynamics model, while the linear subspace, we choose 5 for latent space dimension and linear ODE for latent space dynamics model. As you can see, the nonlinear compression model gave much better accuracy than the linear compression. Nonlinear manifold's worst error was 3.78%, while the linear subspace methods, the worst error was 44%. It looks like nonlinear compression is superior to the linear compression. However, here is a catch. The nonlinear compression requires solving complex nonlinear optimization problems through training, while the linear compression requires some sort of matrix factorization or tensor decomposition, whose cost is a lot less than the nonlinear compression. So linear compression is a lot more scalable than the nonlinear compression. Unfortunately, nothing is perfect. Well, I guess that is why we do what we do, that is research, right? This is it for my talk today. I hope you enjoyed it. Thank you for your attention, and any questions are welcome.